Now we're going to talk about something called strategic dominance, which has a dual role, partly as a solution concept in its own right, and partly as a kind of calculational trick, which you can use to simplify games when you're working with other solution concepts. So suppose we have a player in a normal form game, and suppose we have two different strategies for them. We're going to say that the first one strictly dominates the second one if for every strategy that all of the other players could do, the first one will always lead to a higher utility for player I than the second one. So the idea is that no matter what, there is no conceivable situation in which player I would ever play the second one, because playing the first one will always be better no matter what. It's worth mentioning there's a kind of confusing terminology clash between Pareto domination and the terminology in this video. So when we say domination in game theory, without any extra qualification, we always mean this one by default. Then when we mean Pareto domination, we have to add the name Pareto to kind of qualify it. Okay. There are some kind of minor variants of this idea. So strict domination is the kind of most common standard version of this, but there are a couple of variants. So we can say that xi weakly dominates xi prime if for every strategy profile that you get at least as high payoff, and then there is at least one combination of strategies that leads to a strictly higher payoff. So in this case, we can say that kind of the second thing is not worse than the first thing in every possible situation. And then we have a very weak domination if we have only the first condition. So we only have greater than or equals to everywhere. And of course, each of these implies the next one. So if the strategy strictly dominates another, then in a kind of degenerate way, it also weakly dominates it. And if it weakly dominates it, then in a degenerate way, it very weakly dominates it. So each of these kind of is a refinement. It's a more specific thing to say than the next one. Okay. And we're going to say that a strategy is strictly dominant if it strictly dominates every other strategy for the same player. So what this means is that a player will always want to play a dominant strategy. There is no reason that they would play any other strategy ever. We can also define weakly dominant and very weakly dominant strategies as well. So a thing to notice is that a player can have at most one strictly dominant strategy, because you can never have two strategies that strictly dominate each other. Whereas for weakly and very weakly dominant strategies, this can happen. So it turns out that if every player has a strictly dominant strategy, then that strategy profile formed by those strategies forms a Nash equilibrium, and in fact it forms the only Nash equilibrium of that game. So an example of this is Prisoner's Dilemma. So in Prisoner's Dilemma, it turns out that defecting is a strictly dominant strategy for both players. To say for each player, you can check that no matter what the other player does, they will always prefer defecting to cooperating. And indeed, Nash equilibrium does have exactly one Nash equilibrium, which is both players defect. Okay, so we can do a thing called removal or deletion of dominated strategies. Namely, if a player has a dominated strategy, we can just ignore it. Right? It essentially plays no role in any game theoretic analysis because the player will never play it under any condition. So we can essentially form a smaller game just by throwing some strategies out. So if we have a payoff matrix, you're throwing out rows or columns of the matrix. And it turns out that, so if you delete strictly dominated strategies, this never affects the set of Nash equilibria. So you never lose Nash equilibria. You also, slightly more subtly, you never gain any new ones. So this can be useful as a calculational trick, because if we want to find Nash equilibria of some big game, but it turns out that lots of strategies are strictly dominated, then we can just ignore them and pass to an essentially equivalent game that's much smaller, and then we can calculate the Nash equilibria of that game. A bit more subtly, after we delete dominated strategies, the new game can kind of magically have new pairs of dominated strategies that previously were not dominating. I'll get you to work through some examples of this in exercises. Okay, there's a like a loosely called an algorithm called iterated removal of dominated strategies, which basically means we take a game and we keep deleting dominated strategies, usually strictly dominated, over and over again, until we get a game in which there are no dominated strategies. It turns out slightly magically that for strictly dominated strategies, the order in which we delete dominated strategies doesn't actually matter. We're always going to end up with the same reduced game. For weak and very weak dominance, it's more subtle. By making different choices, we can end up with different games. So we get a solution concept out of this. We say that a game is solvable by iterated removal of dominated strategies, which is a bit of a mouthful, if by applying this procedure, we end up with a game that has only one strategy for each player, in which case it's reasonable to say that those strategies form the solution of the game.